topic over in our unit 5, after you have learned about RNN, is about autoencoders. We have got a brief introduction to autoencoder in this particular syllabus. More of it in more depth you are going to see in your subsequent subject, which is called natural language processing, wherein you go for more models of autoencoders. So here I'm going to share you brief information on autoencoder. So let's dive into autoencoder. What exactly is the need of an autoencoder first? Basically, the need for an autoencoder arises from their ability to address challenges like a high dimensionality, unsupervised learning, noise in data, and the extraction of meaningful features. Till now, whatever you have seen, the models, they were all useful for supervised learning. Okay, especially CNN models. So if you really want to go for an unsupervised learning, then it's better you go for an autoencoder. So high dimensionality challenges will also be overcome with respect to using the autoencoder. Also, the noise in the data could be reduced and meaningful features could be extracted. Basically, they are used with image data. Their versatility will make them valuable in a wide range of application across various domains. So I'll take each of them in detail. So first I'll talk on high dimensionality. In many real-world applications, data can be high dimensional and redundant, especially when you're working with image data, and therefore because of it, it can be computationally very expensive model. There will be many challenges of processing, and there will be curse of dimensionality, of course. So the autoencoder will help you to reduce the dimensionality of the data by using compact representations. And second is, it will be useful with respect to unsupervised learning scenarios wherein you do not have a labeled target, and autoencoders as unsupervised models, they can learn the pattern and the structures in the data without having the need for a labeled examples. So they'll be very useful in unsupervised learning models. Also, extracting relevant features from the raw data is very crucial for an effective machine learning models, is what we have already seen. So autoencoders, they are capable of learning meaningful representations or features from the data. Because the data is unlabeled, autoencoders can very easily extract the representations or the features out of the data, and it can be helpful for clustering or classification. Second is to remove the noise. That is, your real world data is often very noisy, and learning robust representation, of course, is essential. So denoising is required. So denoising autoencoders, they are specifically designed to reconstruct back your data from any noisy input, and they help your model to focus more on essential patterns, and thereby filtering out any noise which is present inside it. Also, the need of autoencoder arises whenever you have got an outlier in your dataset or anomalies in your dataset. For example, particularly in the task like fraud detection or system monitoring, you would be using autoencoders. Second is autoencoders, as I told you, they are useful in anomaly detection because they can learn normal patterns during training, and they can very easily highlight any deviations that are present while testing. Therefore, they are very suitable for anomaly detection. They will be helpful to understand or interpret complex patterns because they are able to extract any meaningful representation out of the data. Also, they will help you in capturing any hierarchical representations, which will help you to identify any structure of the data. Now diving into what exactly is an autoencoder after seeing its need. So autoencoder basically is a type of artificial neural network which is used for unsupervised learning, very important. So its main aim is to learn any efficient representations or encodings of input data for the purpose of reduction in the dimension or the feature learning. Autoencoder consists of an encoder and a decoder, of course the name suggests, and both of them, they are all neural networks. So first, if I talk on encoder will take the input data, it will convert it into low dimensional representation, which we also call it as encoding, or converting the data into latent space. You have to remember this. Encoding is converting your data or representing your data into latent space. So what are you doing here is you are reducing the dimensionality of your data, thereby compressing the input data and representing it more compactly. So Opposite will happen inside decoder. So decoder is going to take your decoder is going to take a low representation, low dimensional representation of a data from the latent state and convert it back into your high dimension. So decompressing operation basically happens in a decoder. So encoder and decoder, they do opposite roles. Now what exactly happens now is we are going to have an objective function also, because training of an autoencoder requires minimization of loss function. Okay, so for that you require an objective function which will be able to measure the difference between the input data and any reconstructed output that is present over there. So we also call that as a loss function, which we have already seen so far throughout the calculation of your backpropagation. So basically for optimization purpose we used it, and the common loss functions are like mean squared error or binary entropy, depending on the application that you are going to use, regression or classification. Now talking on principle of autoencoder. For an example, if you're going for a classification problem, then the network model has to transform the input feature vector of length din to a specific output vector, say dout. So this is the process wherein you are decreasing the feature, that is feature reduction process. You are transforming the high dimensional input vector into a low dimensional variable O. X is converted to O. X is high dimensional, O is low dimensional. So you are compressing your data. So this is nothing but a dimensionality reduction. It has got wide range of applications like data preprocessing, file compression, etc. So basically the first part may you are doing encoding, wherein you are representing your input into latent space, that is you are reducing the dimensionality of your data. So the type of algorithm typically used is a PCA algorithm. That's the most common reduction algorithm basically, and it does use linear transformation, but the ability to extract the feature is of course limited. Now because it is an unsupervised learning, what we are going to do is we are going to use x as your data, and you're going to map it back to x. So f theta is nothing but x mapped to x1. So we are dividing the data, this particular network of f theta, into two parts. That is, the first subnetwork, where we call it as g theta 1, is going to first map x to z, and then z is mapping to x1. We are basically splitting the role of this particular mapping from directly doing x to x, directly converting from x to x1. We are going to use a first mathematical model to convert x into an intermediate result z, and then from that intermediate result z we are going to generate an x1. So what this G is doing, mathematical model, it is doing encoding. So what exactly is happening in an encoding? High dimensional data x is converted into low dimensional variable z. We call this also as a latent variable. So this particular operation here is called as an encoder network, and the opposite operation is happening here, wherein again a low dimensional data is reconstructed as an output, and this is called as a decoder. So encoder and a decoder typically inside one particular neural network is called an autoencoder. That's the principle. So you can see here, this I can represent an autoencoder model. You can see x is converted first into z using a mathematical model gt1, and then suitably using h theta 2, you are going to get back as an x bar, which is a reconstructed output from x. So when they are completely joined together, you form an autoencoder. So if a deep neural network is used to parameterize g theta 1 and h theta 2 functions, it is called a deep autoencoder. Now you can see here one more representation of an autoencoder. You are using input, you are reducing the dimensionality here. This part it is encoding, and then you are creating a hidden vector here. Your dimensionality is reduced to a certain extent here. After this is taken as an input to the decoder, and it gives you a reconstructed output x bar. Correct. So now self-encoder, what it can do, it can transform input to a hidden vector h, z, and then reconstruct x through the decoder. That's an autoencoder. Now we hope that the output of decoder is perfectly or approximately it is able to be very, similar to that of an original input, but of course there will be some errors. So error will be calculated through loss function, where we want to minimize it, of course. So loss function is distance between this x, which is your original input, and the reconstructed output x bar, and you want to minimize this loss function. Okay, so this reconstruction error function is what we call it, and of course it is going to make use of Euclidean distance to calculate. I have already many times explained you what is Euclidean distance. Kindly go through previous videos to understand mean square error using Euclidean distance. So this is what we are using here, mean square error, to determine your loss function here, which we are calling it as reconstruction error function. So I think this was about principle of autoencoder that you have to understand. And in our next class, we are going to see an autoencoder, a type of autoencoder, which we call it as a variational autoencoder.